Okay, I don't wanna find ways to film it with screen recorders, so I'm gonna do it like so. This is a fun example of my cellular automaton, which is a generalization of Conway's game of life, which means it has those cells that can be dead or alive, and also, as it is a generalization, it deviates from Conway's rules in, I guess, 3 or maybe 4 ways. Let's count them. So, first is that there are many species of cellular automata, of lifelikes or life forms as I call them, in one simulation on one sheet. So we can see 2 different behaviors. One of them is making labyrinths and ticking every turn. The other is spreading like a wave whenever it gets some free space to it. Oh no, it died. Oh shit, it died. I wanted to show how they are mutually symbiotically related to each other, but they died. So, one of them is just living, just vibing, and the other is kinda saving them, both or just the labyrinth one. I guess it's the latter way around, because yeah, the labyrinth one doesn't form a stable cycle every time. Sometimes it starts like a, this. Sometimes it starts to recede and leave some free space, and then the more oh, the more reproductively active one starts growing into those holes. And when it happens, the labyrinth one goes after it and basically eats it and fills the gaps again. How is this achieved? How this is achieved? It is achieved by having genomes for every cell. So, for every single cell, there is a genome that consists of 18 points, 18 bits. The first, or the number 0, the index 0, is the living state of the cell. I mean, whether it is alive or dead. And also, it stands in the place of 0 birth, because under the rules of this generalization, I sacrificed the possibility that some cellular automata could be born out of thin air. This is how my generalization genome Oh my god, I don't know English words. This is how my genomic generalization works. The genome itself is stored as a string of numbers, and the state of dead versus alive is one of them. And so whenever a cell isn't alive at the start of a turn, it seeks living cells around it and takes from them, I think we can say, samples of the genome. And what happens next is an interesting process, because it starts with gaining all the information around from the 8 neighbors, and then it filters the information. It filters the neighbors by the agreement on the birth, I forgot the word, let's say birth, I forgot the word, what you guess? It filters its neighbors by the birth rule. How? Just by the number of the neighbors, by the quantity. It filters only those neighbors who agree to give birth at that quantity of neighbors. And so from those chosen neighbors, it combines its genome by basically choosing a 1 or a 0 for every point in the genome by randomly picking from one of the parents, let's call them that. So if we have here, what do we have here? We have this precious thing I call a zebra. We can see it zebraing around, and this little thing, it has all the same but plus 1, another one added. And this red thing here is missing one. It is missing the birth condition on few neighbors. And just like so, the cells can be born here with different genomes based on the combinations of those. I think the cyan one will dominate here because it has more birth conditions. I think it is a very straightforward survival characteristic. More birth conditions means more births, more reproductive activities. More reproductive activity means more reproduction, I guess. So it is winning here. But we can find maybe something where it isn't so obvious who will win. Maybe this one. So it also means The genomic principle, the genomic rule, also means that some of the species are not breedable together if they have different and entirely non-intersecting sets of birth conditions, then they are not breedable together because, well, they can not end up in the same filtered parent list, let's say. So when a cell is about to get born, it filters its possible parents by the number of those possible parents, and by this, by definition, it can never filter two species with non-intersecting birth condition lists together. And by this very principle, species with different birth conditions cannot be bred together, and what's more important, they can live together without crossing into one, like here. Yeah, this is a colony, and we can also put here a virus, which will form something like a boundary, but it doesn't really impede the growth in any fashion. So it will just be crushed by the colony because it grows, and the field, the game board, just loops, and so its two ends are crushing onto each other. Also we haven't here the more advanced rule. Let's take it away and try it with a more advanced simulation to showcase another funny thing I had to add. Maybe now it will show something different, something interesting. Yeah, okay. Now it is kinda less survivable. It is visually pruning, I guess. This is because I can turn on or off my another rule I call what do I call it? I call it SUST because I thought it is like sustainability, sustaining, or sustenance, I guess. It means that for a cell to stay, it has to have neighbours, and not only neighbours, but I think 3 layers away of cells that agree on that staying. So of cells that have the same stay condition as the condition it is going to use. So if a cell has 5 neighbors and it thinks it will stay, as it has the genome with a point on 5 on S5 exactly, it wouldn't stay if the random picker picks a cell around that has not the as 5 criteria, or it can pick a similar cell that has that criterion, and by this continue to live. But it doesn't happen always, and one of the simulations, one of the combinations of cellular automata was the thing I showed at the beginning, was this thing where the, let's say it, ephemeral life form here, ephemeral I mean like the plants who live only 1 year. Here it lives for only 1 turn and then dies but spreads onto the neighboring cells, essentially switching back and forth. It has no state conditions, and by this it can kinda predict, kinda hunt down those cells who can actually stay. Those yellow cells that remain in some areas, which can stay at 0 or 1 or 2, 3 or 4, as it states here, under 0 to 4 neighbors. And here we have the labyrinth one recede because it cannot hold its frontiers, cannot expand itself, and when it recedes enough, the yellow thing breaks loose and fills the world again, helping the labyrinth life form also spread with itself. And the cycle goes on and on, but unfortunately it doesn't really display some sustainability. I mean, it can easily just die out. Just all of those spores can die or malform, so they just don't stay. But if they do, if they manage to survive, I think they are not really in any danger after it, because it's very cyclical inside and quite predictable. I think this one here won't ever be distracted. Oh, I guess I know why. Because it's stabilized. I meant if I can make an artificial hole that will grow outwards and then manually clear any growth, I think I can bet on any of those little cells, little spores, that they will survive long enough. Yeah, that one did. That one managed. This one, let's see. Yeah, it also perfectly manages to live. But what happens if I turn off the sustain rule? Yeah, the breaking of the yellow thing loose is happening even inside the labyrinth. And after it is formed, after it has broken loose, we can see it isn't quite eaten by the labyrinth. It just kind of mixes in, or even becomes part of the labyrinth. Yeah, it kind of formed another labyrinth. Didn't think it could be possible at all. Let's watch it a little. Oh, I guess I know what's happening here. I guess I know why it's also disconnected. Yeah, sure that was going to happen. And this is a third rule of generalization, which I had to introduce. Oh, oh no, the labyrinth species has almost died, but not really died. It still is here, but not so dominant. That's fine. Let's turn the source model back and see what's going on. Let's see what we... I guess they are not very keen on going back to that exploitation state. Oh my god, what's that outside? Yeah, this doesn't work anymore. They can't exploit the weavers as much as they did before. Oh, okay. Now they do. Now they are eating the weavers and they are eating their way back or not? No, they aren't. They are not, I guess. It's a weaver's revolution. Yeah, absolutely. So what is this red view? What is this infrared heat camera? Actually, it shows the age of the cells. So if we turn it from the beginning, the field is white, but there are some cells that are becoming visible. They are the cells that live continuously, the cells which can survive under their rules. Here it is 29, the age of 29 turns. And here, under the age scope, we can see them in red. And also we can see them disappear. And if we turn off the SOST thing, we get to see more of them appearing here. Maybe more, some more, just a bit more. Or those, yeah, exactly. What does the aging do other than track the time? It does some interesting things for the evolution, because if I turn aging, oh, I didn't everything to implement a rule to turn aging off. Actually, I think I got to do it. Or no. Or maybe I don't. I don't do it. I just add here the regular Conway's game of life. I'm adding the regular game of life here just to show what aging does to the regular game of life. So the game of life has its birth condition 3 and its day conditions 1 and 1, 2 and 3. Yeah. Let's also make a second game of life here because the generator at the beginning requires 2 species. Well, this is a single species. This is game of... No, it isn't. Because I didn't make it alive. Let's make one of them alive to see the difference between alive and not alive. Yeah. The one that's not alive isn't alive anymore. I'm not sure about this. Let's try again. I don't really remember why it happened that way, but it was a version in which it happened that exact way. So here we are back to normal. We are back to live. Here we have some of our basic blocks, our basic boats, our basic still. Oh, it's a glider. Yeah. We have our blocks and boats, and I don't remember this thing. And now we go to the heat cam, to the age cam, and they are increasing in red. They are increasing in red until... What happened? Oh no, what happened here? They aren't there anymore. They just aren't there. But the heat from the aging still is. This is made for the explicit purpose of keeping away the thing that you can see here under the mutations. If I turn on the mutations, first there are some of those things, some of those conquerors which made a mutation that allowed them to reproduce at all cost. Oh no, goodness. At all possible times, and then they get replaced by things that can reproduce a little bit more, by noodles, and then by zebras. Is it a zebra already? Oh, it's coming to a zebra. Yeah, let's see when a zebra emerges. Here maybe? No, it's not. It doesn't have one of those, but it's pretty close. And functionally, I guess, identical. Let's see if anything like this is a zebra. No, nothing is a zebra here. Here we have those mutations bring up more and more reproductive species, and as they grow in reproductive activity, they start to reach the limit. They start to fill their genome with ones. It's not very visible, but here they only have 0 for birth at one neighbor, which isn't very relevant given the density, and they lack the birth at 8 neighbors, which is quite visible as they have this spongy structure. What happens next? What happens if they get all of the birth conditions? What will they compete next for? Let's see. Let's see for ourselves. And also sometimes go to heat cam, to the age cam, and see if anything changes here. Yes, something is definitely going on. What's that? Yeah, some of the cells are staying for long. They are staying longer, and what's this exactly again? Give. Oh no. I love, I love this effect. They stay long enough and then just explode. Yeah, they explode, and the exploded area was originally supposed to be uninhabitable, but then I tweaked it around, round, for some time, for a while, and ended up somewhere here with the rule that sometimes cells can inherit that overaged space if they have a lighter genome than the thing that died here before. And it kinda works, but it kinda reaches an equilibrium also. But this is the third rule here. So the 3 rules I added to the cellular automaton were exactly like so. First is genomes, genes, and it's a virus. It's a little virus here. Look, it's a virus. It isn't alive, but it reproduces still. It reproduces and it doesn't die away. It lives without being alive, actually. So nice. So the first rule is genomes and genes and the reproduction cycle with that filtering thing. The second rule is that to stay, they have to get an agreement from their neighbors, or more likely, to stay, they have to randomly hit an agreeing neighbor. And the third one is this, the aging that prevents this thing from happening. If I make the death age really high, like higher than what we have here, we will see how horrible it looks without a death. It is just a solid wall of cells which don't go away in any reasonable way, and it just stops evolving from that point. It just stops anything because it is all cells which have no dying condition. They just stay at any number of neighbors, and so they just clutter all the mechanism of the system. They stop it. Is it a zebra? No, it's not a zebra. Well, technically I can tell this is a zebra, it may be, but no. It's not a true zebra, it's not the true zebra. Is this? No, it's not. Is this? Oh, it's almost a zebra. What about ages? No, all the cells are new and some of them are even staying empty. Okay, what's this? This is a square zebra. This almost completed its birth condition, so it is gonna start working on the stay conditions and so become this thing. Yeah, of course. Does it breathe itself into existence? Yeah, like exactly. It just wins the competition by breathing itself into that population and just clutters the system, makes it stop. So yeah, basically this is what we get if the cells don't die. And this is why I added the aging system, to make the cells go away sometimes. Oh, new thought. What if we put here the sustain rule? Oh, something moved. Something is moving. But yeah, not very much. Can it evolve into something lightweight though? What if it can? Can we imagine that? It is wobbling a little bit. Maybe, just maybe some of the cells luckily get destroyed by the rule of sustaining. I guess they won't, but still maybe. Let's wait for some time. And oh, so red. What is it? 600. And the dying age is 1,000. Can we wait till it is 1,000? Let's try. It's not really a minus. It was a minus when I when I picked an empty cell and it didn't erase properly. So okay, let's wait until it is. Yeah, here we have a proper minus and the gray cells, and here we are waiting. We are. Whoa! It all exploded, and they all immediately they immediately started eating on themselves because well, the red age is so high that any cell has enough genome lightweightness to conquer the land, to claim it back. This is why it doesn't really work with too much of a high age, and it has to be fiddled to create an environment that will support evolution of some interesting forms. Also, if I could find this, I think I'd like to show another one of the cellular automata. Oh, I mean the colony, the automaton that can use viruses as a means of recolonization. Or maybe I won't. No, I won't show it in this video. I'm gonna just say goodbye and leave.